Okay. Hi, I am Jessie Grimm, and I am presenting on the flow distribution experiment. First, I want to go over what my presentation will entail. There is going to be the objective, the theory, the apparatus, the procedure, the calculations, the results, and finally, the conclusion. First, the objective. The objective of my experiment was to study any deviation from ideal flow conditions, to use the axial dispersion model, and to find the apparent longitudinal diffusivity, or DL, and to compare a plug flow reactor to a continuously stirred reactor using that DL. Okay, so the theory. The axial dispersion model is the theory behind this experiment. It is an equation that describes behavior of tubular reactors. It assumes fluid velocity and concentration are constant against the diameter of the reactor, and it also assumes a well-mixed system. Now, the variable that we care about in this equation is DL. And it is a variable that accounts for mixing both by molecular diffusion and by fluid movement. And DL for a PFR is equal to 0, and DL for a CSTR is equal to infinity. Which I will get back to that later. Continuing with the theory, here is the actual axial dispersion model equation, and all of its variables defined for you. So moving on to the next section is the apparatus. Here you can see a schematic of the apparatus. There are two tanks. One contains tap water and one contains our salt solution. A pump flows the fluid from one of these two tanks into the bottom of the reactor, and it exits out the top of the reactor. So here are actual pictures of my apparatus. This is the simulated reactor, which is simply a column filled with glass marbles. And you can see on the left the 4 conductivity probes. Next we have a picture of the pump. And finally we have a picture of the 2 tanks. Now the procedure for this lab was very simple. First we flowed salt water into the bottom of the reactor until it filled up to the top. And then we switched over to regular tap water and allowed it to push the salt water out of the reactor and fill it up. And after it had finished doing that, we switched back to the salt solution. During each of these trials, we measured the linear velocity 3 times, and we took the mean of those 3 numbers to use in our calculations. We recorded the conductivity versus time using the data logger. Also, I'd like to note here that there were no safety issues with this experiment. If different chemicals were to be used rather than water or a salt solution, you would have to take precautions, but with this particular setup, you don't have to. So, moving on to how our calculations were completed, this is an actual excerpt from the lab handout. It was a lot cleaner looking than our completed Excel sheet. This table was inserted into Excel, well, it was created in Excel, and the experimental data was inserted into the appropriate cells. The model values were calculated from this equation, and then we subtracted the model values from the experimental values and squared them. And how DL was found from all of this was we used solver to find a DL that minimized the value of the sum of the errors squared. This was completed twice for each conductivity probe, once for the inlet and once for the flush. And that means that for conductivity probes, we had 8 values for DL at the end of the experiment, which can be seen in this table here. And returning to what I said earlier, DL for a PFR is equal to 0, and DL for a CSTR is equal to infinity. And if you look at our table of values, you will see that the input values simulate a PFR because they're smaller, and the flush values simulate a CSTR. And we believe this is due to differences in density between the tap water and the salt solution. And continuing with the results, we have plotted the experimental values versus the model values simply to show how well the axial dispersion model equation fit our data. There's a graph for each probe and each calculation for each probe, so that means there is an input and a flush graph. So here's probe 1 and probe 2, probe 3, and finally we have probe 4. So in conclusion, the axial dispersion model was able to simulate our experimental data quite well. Our input DL values were typical of a PFR, while the flush DL values were typical of a CSTR. Any questions?
Your graphs were